thanks everybody for joining today. We're gonna have a great session. This is actually a talk that I've given this talk a couple times, but not even near the length of understanding or depth that our speaker can actually give it to. So I do hope this is valuable to everybody, but thanks for taking the time. We do like to tell everybody if this session is going to kind of be beginner, intermediate, advanced. I kind of gauged this session today to be intermediate to advanced. And that's really the topic here. We're going to dive into the architecture of CockroachDB and how we actually do what we do here. But also, our guest today can get as deep as y'all want to go. He is the CTO of our company. So that said, we would love to have questions from y'all. I think we're going to take the top 5 best. Oh, people aren't hearing my audio. Can you guys hear me in the thing? Can you guys? Yeah. Okay. Great. There was only one person not hearing my audio, so man, thank God. We're going to take, I think, the top 5 questions, and then we're going to give away a copy of the definitive guide to CockroachDB, which actually Peter could have written if he was Shakespeare, but man, it takes a lot to write. Our other founder, Ben Darnell, actually helped write that one. So, and the recording will be available just after the session. So with that, Peter, I'm going to ask you to come on video as well here. Hi, Peter. How are you? I'll wave. I'm sitting next to Peter, y'all. So, y'all, I'm happy to have Peter Mattis join us today. I've known Peter for a couple of years. I've had some really amazing conversations with him. And learned a whole lot along the way about distributed systems and the architecture of CockroachDB. And he's going to do this presentation today. What I have up here on the screen right now is I think your last 6 or 7 years of.
That's what it looks like. 7 years of Git contributions.
And that's a lot of time and a lot of contributions.
Yeah, it's pretty cool to see.
But it seems like you were doing a lot of commits, and these days it's a little bit more code reviews.
Yeah, it's definitely slowed down over the past 6 months.
That's what happened. So so just a prolific developer, I think one of the leading minds in terms of distributed systems and some of these things. So, but I'm Jim. I'm principal product evangelist here. I'll be maintaining the chat and logging questions into Peter at the end and whatnot. So please do ask questions in the chat, in the QA. We'll get to them in the end. But with that, I'm going to cede the floor to you, Peter. So have at it. All right. Thanks, everybody.
Thank you, Jim. All right. So a little bit why are we here today to talk about the CockroachDB architecture? When my co-founders and I got started on CockroachDB 7 years ago, we were taking a look at the database landscape, and we knew about the legacy databases that had been designed, 30 going on 40 years ago, and they were designed in a different era. And then from the legacy databases, in the aughts, we moved into the NoSQL databases, then, cloud augmented legacy databases. Where we are today, the world where we're at today is we have distributed SQL databases, and CockroachDB is, in my opinion, the preeminent example of a distributed SQL database. It takes advantage of cloud native architectures. And what I'm going to talk about today is some of the major architectural components of CockroachDB. I need to caveat this, which is the CockroachDB architecture is incredibly complex, and I'm not going to be able to get into any serious level of detail. What I'm hoping to do, though, is give you an understanding about some of the decisions we made, and this can, help you have a better understanding both of Cockroach, but also distributed systems in general, because we have distributed applications being built on top of distributed databases. Understanding the architecture of the distributed database can inform your decisions for a distributed application. So with that out of the way, let's get started. So distributed SQL, what do we mean by distributed SQL? Well, one, we feel it's really important for a database to implement the SQL standard interface, and CockroachDB does. Why SQL? It's kind of the lingua franca for languages to access data storage. Now there's alternatives that are coming out, and NoSQL kind of famously eschewed SQL, and now they're kind of backtracking on that. And those NoSQL systems have been adding SQL-like semantics over time. We feel that they're still playing catch up. It would have been better just to embrace it from the get-go. Distributed, this eases operational complexity at scale. I'll talk about this a little bit more in the subsequent slides. CockroachDB is geo-replicated. It's always on. It's resilient to machine failures and region failures and environmental changes. Because it's SQL, we implement ACID-compliant distributed transactions. These are fully general transactions. And then it's geo-distributed and ties data to location. We can't fight the speed of light. We can't beat the speed of light. And that implies certain latency lower bounds if you're having to cross the world to access your data. So you need to move the data closer to where the application and the users are running. CockroachDB is fundamentally architected for the cloud. We feel this is a better architecture for your developers and your applications. It exposes itself as a single logical database, even though it's composed of individual nodes. Now, the individual nodes, they join together just seamlessly. You don't notice that there's individual nodes taking place there in your applications. And then it gives you that familiar SQL standard interface. In order to scale up the database, you simply add more nodes. And this is really simple. You connect the node to the database, and in the background, CockroachDB is automatically rebalancing and moving load around and resources around, and there's no manual work required. You can also do this not just on the scale up, but the scale down. Oh, something changed in your application, you no longer need the capacity you had, scale it down, and CockroachDB just automatically adjusts and handles that. And this removes this incredible operational burden. You can actually scale not just within a single region, you scale out across different regions and even across different clouds. We have customers running across multiple clouds now, and you still get that same single logical database behavior. Now, as I was mentioning earlier, there's this natural resiliency to this distributed architecture. If a region dies, nodes die, the system just automatically recovers this. And you have this always on behavior, zero RPO and RTO in the common cases. And this also allows for something that's extremely important from a maintenance perspective. We do rolling upgrades with zero downtime. You can roll out a new version of CockroachDB and experience no downtime. We've also heard, and we're continuing to hear multiple reports from customers that when they're testing CockroachDB inside serious production systems, you have to actually simulate failures. And what happens when you simulate a failure with CockroachDB? Well, it turns out it's a nothing burger. Nothing happens. The system just keeps on running. In contrast to that, with traditional legacy setups of kind of primary, secondary failover, I mean, those systems are getting paged when they're testing this. When in those same companies, when they're testing CockroachDB, nothing happens. So as I've mentioned multiple times, what CockroachDB exposes is a single logical database. And what this means is that when you're actually doing queries into the system, you can do the query into any node in the system. And even if the data is not located on that node, CockroachDB internally routes the query and retrieves the data from wherever it's located, even if it's located in a different region across the world. Now, doing that kind of cross continent, transatlantic kind of query, it's going to impose some kind of latency. And so there's actually facilities in CockroachDB that you can geolocate the data for a user near where the user is. And we also have automatic systems inside CockroachDB that attempt to move data close to where it's being accessed. And you might want to do this both for the latency benefits. That's extremely important for global applications. But there's also compliance regions. GDPR is a real thing, and there's similar regulatory requirements coming up in other areas nowadays. And this is an increasingly important region to do a geolocation of data. All right, so here's the agenda for today. I'm going to talk through each of these sections and kind of they build upon themselves. You'll see about how kind of the fundamental architecture of CockroachDB works. So kind of like the base thing that I like people to understand about CockroachDB is internally there's this monolithic logical key space. You can imagine that all the table data, it's all stored in this one monolithic logical key space. And over subsequent slides, I'm going to explain how this works. But just imagine all the data in some CockroachDB cluster was in this single dogs table. Essentially, you get this monolithic key space. It's ordered lexicographically by key. Now, I want to just mention briefly that you probably had this question. Well, you said it was a SQL database. SQL has, this kind of complex data model. How is this mapped onto a KV store? Well, first, put aside the SQL part. Just understand that this KV store exists. It's not exposed externally. We did that intentionally. We didn't want to add to the kind of cognitive complexity of understanding CockroachDB. Externally, it is SQL, but internally, there's this KV store. The KV store has a number of primitives, powerful primitives, but a handful of them. You can get keys, you can put a key in a value, there's conditional put operation, you can do scans, and you can delete keys that already exist. The KV store, this kind of separation behind having a SQL layer and a KV layer, it allows our internal teams to focus. We have a team that works on the KV store separately. their tasks. They worry about distributed transactions. They worry about the replication of the database. And then the SQL team worries all about SQL execution and optimization. How do we map the SQL data to a KV store? So all that's tabular data that's in SQL is stored as this monolithic sorted map of KV pairs. And I should mention in CockroachDB, all tables have a primary key, which isn't true of some other legacy SQL databases. Well, underneath the hood, they usually have some form of primary key that might be hidden. And this is actually the case inside CockroachDB as well. If you don't specify a primary key, we provide one for you. Now, each row in the table actually maps to a single key value. And these key values, they're strings. And you can see a little bit of like this, kind of conceptual view of what the key looks like. A key is composed of the table name, the index name, and then the key itself, or the key values themselves. And then the value is this, essentially a comma separated list, conceptually a comma separated list of values. It's actually a little bit more complex than that practice, but conceptually, this is what it looks like. I want to walk through a little example of how this actually kind of plays out in practice. So what I'm showing on the screen here right now, we have this inventory table that has 3 columns. The primary key is this ID, and it's some example data here below where I show 3 rows from this table. And the ID column, the primary key is highlighted in blue. And you can kind of imagine what does this translate into for keys and values? Well, the key is going to need to contain that primary key column value. So we see 1, 2, and 3 for the keys. And then the values are just what you expect. They're the column values, the non-primary key column values. As I mentioned before, though, we actually put a prefix on these keys. And that prefix is the table name and the index name. So that looks like this. The table name is inventory and the index name is primary. If you actually went and created a secondary index on this table, this would actually create a whole new set of keys and values. And it's important to understand that this takes place. Creating a secondary index is kind of a fairly heavyweight thing to do on a table. I should also mention, this is not unique behavior to CockroachDB. Every SQL system, when you create an index, that index has essentially a row in the index for each row in the primary table. And what does this look like? Here I created an index on the name column. So we see the keys look like the table name, inventory, index name, by name, and then we see that the index column there, the name, as being the suffix of these keys. The value in these secondary indexes is actually the primary key. So here, ball, the primary key for the ball row is 2, and we see that showing up as the value for the index on ball. I should mention what I described here is a little bit of a simplification. There's actually additional complexities. For one, we actually don't store the table name and the index name as names. That would actually make it prohibitively expensive to rename indexes and to rename tables. So what's actually stored under the hood is IDs, and the IDs are prefix compressed. And there's a lot of compression techniques that take place here. There's a ton of additional complexities. One of the biggest ones is the handling of null values. Null is this kind of just complex concept for most people new to SQL to wrap their head around, because null does not equal to null. I'm not going to get into that now. Just be aware that this can be handled just through the key encoding. There's also complexity of handling non-unique indexes and storing clauses. The high-level point to take away here, though, is that there is a mapping between SQL data down to KV data. And something else I want to impart here is CockroachDB is doing this. It wasn't doing this in, this wasn't a super innovation of anything CockroachDB does this. Other legacy SQL databases, any that are row-oriented, are also essentially at the bottommost layer KV stores. They'll have something like B trees at the bottom layer or some kind of heap record. And those are essentially key values as well. The keys actually happen to be composite, not just strings, but there's really no conceptual difference. All right, so back to our monolithic key space. The monolithic key space is just logical. Physically, that key space is divided into contiguous 512 megabyte chunks that are called ranges. And I should mention that the 512 megabytes, it's not like a strict oh, these ranges, they always occupy 512 megabytes. That's actually the target size for the range. It's the max size for the range. Ranges are small. That 512 megabyte size was actually chosen as a balance between two competing demands. On the one hand, we want to be able to move these ranges around in a cluster quickly. Moving ranges around in a cluster quickly allows us to rebalance for load. When a new store comes on, a new node comes online, we can rebalance nodes onto there. But we also want to make them small enough or large enough that we minimize and amortize the indexing overhead. So these ranges just don't sit out there, kind of floating unattached. There's actually another indexing structure that sits on top of these ranges that allows us to locate them. This indexing structure is itself another range. This is kind of recursive. So we have the ranges that store the data, and then we have these meta ranges that store the indexing structure. And there's actually another range that sits on top. This is a two-level indexing scheme. And if any of you in the audience listening today are familiar with Bigtable or Spanner or HBase, this is very analogous to their two-level indexing structure. And if you kind of squint, this is very much like a B tree structure. A B tree has kind of arbitrary depth. This is a fixed two-level indexing structure. Now, the ranges in this indexing structure, they actually enable something that's super important to implement SQL. They enable efficient ordered range scans. So if I have something like this fragment where I want to find all the dogs that have names, greater than equal to Muddy and less than equal to Stella, I can do this. I can consult the indexing structure. That points me to the two ranges that have keys of interest, and I directly go there. In this case, I'm actually accessing 2 out of the 3 ranges in the system. But in a real production CockroachDB instance, you'll have thousands or tens of thousands of ranges, and this will point you directly to the small subset of ranges that are of interest to your query. Operations that update the ranges, they're transactional, and I'm going to get more into how the transactions are implemented later on in this talk. Suffice it to say, if you want to do an insert, here I'm showing an insert of a Sunny record. What we do in order to do the insert is we have to consult the indexing range that points us to the actual range that will contain the data. We go to do the insert there. We do a check. Is there enough space available in that range to insert the record? If there is, we just do the insert, and voila, the new record is present. And then the other common case is if we want to insert. Here I'm trying to insert another record, Rudy, into that same range. And oh, lo and behold, the range is full. So what do? Well, the range essentially gets split in 2. And we split the range, create a new range, a sibling range. It gets half the records. You notice that the records are still ordered within each range, and that the ranges, they do not overlap. And then we update the indexing structure to point to the new range as well. And after the split takes place, we perform the insert. That's actually slight inaccuracy. We actually perform the insert, and then the range is split in the background. Small details. All right, I'd like to move on and talk about Raft now. So Raft is a distributed consensus algorithm. Those are fancy words. If you're familiar with this area, the other big distributed consensus algorithm is Paxos. And we use Raft to perform replication. So each range in CockroachDB is actually a Raft group. And each Raft group has a number of replicas that actually implement Raft. And by default, we have 3 replicas for each range. With quorum consensus algorithms, you actually want to have an odd number of replicas in your Raft group. We use 3, you could use 5, you could use 7. And what that gives you is you get quorum rights. And the quorum rights are, the right is complete when a majority of the replicas in the Raft group have accepted or committed the right. Raft is itself, it was supposed to be a simplification of Paxos. Kind of my opinion is, they're both quite complex to implement. They're complex to implement in toy scenarios, though plenty of CS students are now doing this in university nowadays, which kind of shows you the progress in computer science. It's implementable by a CS student in a class, but actually making it production ready is significantly more difficult. Due to the architecture of CockroachDB, one of the challenges we have is by default, Raft has its own concept of liveness, but we can't use that Raft liveness. There'd be too much traffic in the system. So we have a concept of node liveness, and then we attach the Raft liveness to that node liveness. And then the other thing we do is part of the Raft liveness that still has to take place is Raft is sending out heartbeats all the time. And just that heartbeat traffic would be overwhelming. So we actually coalesce heartbeats in order to make it more efficient. And then the final significant optimization we added to Raft is that in a large database, most of the ranges are not seeing any traffic. So we actually quiesce. We have this idea of quiescence where we quiesce the Raft group and it doesn't do anything if nothing's going on. I mean, this is what you kind of expect. If there's nothing taking place on a range, no activity, it doesn't need to be sending any background traffic. Now, one of the very extremely useful properties from consensus algorithms that we utilize within Cockroach is the ability to perform writes atomically. Essentially, when you propose a write to Raft, Raft is either going to accept it and it'll commit it and it'll be durable and you know it's going to be there, or it will fail it. You don't have this in-between state. Now, this is like the kind of conceptual way that you interact with Raft. Inside Raft, Raft is having to deal with all the different failure states, and that's what makes these consensus algorithms so difficult, because the number of failure states is actually quite large, and handling all the different states is the real meat and potatoes of what Raft does. Inside a Raft group, a single replica is elected leader. And a lot of the complexity inside Raft is making sure there's only a single leader at a time, and if the leader fails, another replica will get elected. The leader replica is what coordinates all the writes inside Raft. It's proposing the commands to the followers. In CockroachDB, we also give it another role. The leader is the only replica that's allowed to serve authoritative up-to-date reads. And it can do this serving of authoritative up-to-date reads because it's been proposing all the writes to the Raft group. We also allow the followers to serve reads, but the followers only can serve stale reads, not up-to-date reads. But those stale reads are still consistent. And there's a whole other subsystem within CockroachDB that enables us of serving these stale consistent reads. It's accessed via this additional syntax we added to Sql, where you can query as a particular system time, and you can actually dynamically determine what that system time is so that you can actually read from followers. This is extremely important for geo-distributed databases. It's really an interesting part of it, and I can't say any more about it today because it's a really in-depth topic. Now, I mentioned that there's this atomic writes that happen with Raft. And this is actually something that's an extremely important building block for transactions. So we do a write into Raft, and the command is proposed by the leader to the follower replicas. It's distributed to the followers. The write is only accepted when a quorum of the followers, the majority of the followers, have acknowledged receipt of that write. And this is what that atomic replication is. This is a building block that I'll talk about in subsequent part of the talk for our distributed transaction implementation. There's a lot more to say about Raft. It's pretty fascinating, and there's a number of really nice visualizations and tutorials about how Raft works. One of the better ones we've come across is this one at thesecretlivesofdata.com. And if you're interested in this topic, I highly recommend you go check it out. Some of these visualizations are awesome. People put enormous work into them, and they can really give you a great mental model for how something like Raft works. All right, moving on. So, I talked about our monolithic key space broken into ranges. The ranges, each range is a Raft group. Each Raft group is backed by some number of replicas, typically 3 replicas, maybe 5 replicas. But then we have this, kind of question. We have all these replicas in a CockroachDB cluster, thousands, tens of thousands. We have some that are pushing north of 1 million nowadays. And these replicas can actually be placed anywhere in the cluster. And so we have this question, almost a problem of too much flexibility. We can place replicas anywhere, so where do we place them? Actually, I think of this very analogously to the omnivore's dilemma. We as humans can eat anything we want, so what do we eat? Well, there's actually important, heuristics and signals that we use to power how we place replicas. And we use 5. The first signal we use is user constraints. Users can specify for a particular table, a particular database, or even a partition on a table or an index on a table where the replicas should be constrained. And you might do this for performance reasons, for geolocation. You might do it for business requirements. EU data needs to stay in the EU, something like that. Or you want, West Coast user data to stay on the West Coast for performance reasons. The next signal is space. You want to balance the disk space across the nodes in the cluster. And you do this so that you can take full advantage of disk space, but disk space and disk utilization also has a correlation to the disk accesses. You want to balance the disk space across the cluster so that when a read comes in, you can actually get more of the aggregate disk IOPS and disk bandwidth for performing the read. Diversity is the next signal. And diversity is about spreading the replicas across the various failure domains within a cluster. What is a failure domain? You might not be familiar with that term. Well, a failure domain is just a unit that can fail all at once. Like a disk is a failure domain, a server is a failure domain, a rack in a data center is a failure domain, the data center as a whole is a failure domain, a region containing multiple data centers is a failure domain. I mean, eventually, if CockroachDB ever spans the solar system, the Earth will be a failure domain. I mean, you can see like what the concept means. We're trying to spread it out across as many failure domains as possible. If you only have your CockroachDB cluster in a single region, we're going to be spreading across the racks in that region. If you have a multi-region cluster, we're going to be spreading the replicas across the multiple regions. But we're doing this while still adhering to the user constraints that were specified. The fourth signal is load. We want to balance the load across the cluster. This is pretty easy. The load is kind of correlated with the space balancing, but it's not perfectly correlated. And there's plenty of example workloads that demonstrate this, where you'll have a single hot range, and you want to isolate that range onto one node so it's not doing other work. And the last signal is latency. We try to move the replicas close to where they're being accessed. So let me talk through this just a little bit more. I mentioned the diversity. I mentioned failure domains and some of the typical examples of failure domains. If we have here an example, 4-node cluster, these are just nodes. Each node is a failure domain. We're not going to put multiple replicas of a range on the same node. That wouldn't really make sense at all. I mean, that's actually a failure domain constraint that's pretty strict. It never makes sense to put multiple replicas on the same node because it's quite likely that that node could die, and then you wouldn't actually have any resiliency to that node outage. Because each range has a separate set of replicas, we can actually choose a distinct subset of nodes to put those replicas on. And this is kind of important, an important concept to kind of drill in. We're doing replication at the range level, not at the node level. And this is a distinction from some of the systems that came previously before CockroachDB arrived. They would do replication at the node level, and if a node dies, you have to re-replicate. There's only a handful of other nodes in the system that'll have the replicas. In the CockroachDB case, the data is spread out, and if a node dies, there will actually usually be replicas on the replicas. Remaining replicas will usually be spread out throughout the remainder of the cluster. Next, I want to talk about load. The load-based replica placement, it's actually watching for the traffic on a range and on all the ranges that are on a node, and then gossiping all this info amongst the cluster, and then trying to redistribute the ranges so that each node in the system is actually handling equal load. And the reason for doing this is purely clear. It allows us to get better utilization of the cluster. It avoids one node becoming super hot and a bottleneck for throughput or latency on the system. And lastly, to talk about replica placement, latency and geopartitioning. There's actually two ways that we take advantage of latency and replica placement. The one is about user constraints. So users can indicate, I want to constrain this replica placement to some location. And there's actually even two ways that we allow the user to specify this. They can just specify that, oh, I want this index constrained to an area. And if they're doing that kind of constraint, it's just purely done based on moving the replica to the location we want to constrain it. They can also specify this constraint via putting a prefix on the key. And this is kind of something that's interesting and like an interesting principle. We have this logical key space. How we actually construct the keys, we can take advantage of that for various locality purposes. So let's say, we have this dogs table and we say we have EU dogs and US East and US West dogs. Well, we can tag the location, like the preferred location for all these dogs by putting a prefix on the keys. And here you see, EU, US East, US West. And with that prefix, it kind of co-locates all the data for the European dogs and US East dogs and US West dogs, and then combine that with the further constraints, then we can say like, oh, hey, that range containing the European dogs, well, actually constrain that to Europe. There's another latency signal we take advantage of, and this one occurs automatically. We'll notice where the reads for range are coming, and if they're all primarily coming from one location, we'll proactively try to move one of the replicas and the leader replica to be near where that load is coming from. And this just happens behind the scenes. It's called follow the sun inside in some of our documentation. And this just automatically adapts to the traffic. So those were the replica placement heuristics. But there's also various mechanics that take place with replicas. And I'm going to talk through a little bit how replica rebalancing and handling failures occurs. So here I have now a 5-node cluster. It's just a new 5-node cluster with a new node just getting added. And we have a handful of ranges, 3 ranges that are divided up amongst the previous 4 nodes. When this new node gets added, what happens is the Raft leaders, they're sitting on the other nodes, they'll notice that new node and they'll make a determination. Hey, look, there's this new node. It has less disk space utilization. I'm going to actually move one of the replicas over to this new node. And that movement, as in all things computer science, you never actually move anything. You actually create a new replica, and then you remove the old replica. That addition of the new replica and the remove of the old replica actually occurs atomically. There's just a single atomic Raft operation to add the new and remove the old. Voila. Now, another common scenario that happens in a Cockroach cluster is that you lose a node. And there's 2 scenarios here. The first to talk through is permanent loss of a node. Node catches fire, goes up in smoke. Data on it is permanently unavailable. When this happens, the Cockroach cluster notices this, the remaining nodes in the system notice this, and they will perform proactively without any user involvement. They will up-replicate and create a new replica so that they get back to that full replication state. There's another type of node failure, and this is actually the more common type of node failure, where node is temporarily down. Someone accidentally unplugs the server. Well, maybe that doesn't even happen that often. The servers crash. Servers crash, processes crash. When that happens, we have a temporary blip. And that blip might last from 30 seconds, might last for 10 minutes. We don't want to perform full up replication in that case. What actually happens is that node comes back, we will actually catch the replicas up to date based on sending logs of operations that occurred while it was down. And this is much more efficient than sending the full replicate data. Sending the full replicate data, you might have to send a terabyte of data to up replicate. Sending the logs can be a small fraction of that, tens of megabytes or 100 megabytes. All right. I'm going to move on and kind of tie some of what we previously talked about together into how CockroachDB performs transactions. A little bit of background, these are ACID transactions, and you can see up here, we're talking about atomicity, consistency, isolation, and durability. We decided early on at Cockroach Labs to embrace serializable isolation. Serializable isolation is basically the gold standard isolation level. And kind of the intuitive mental understanding of serializable is it's as if the transactions are run in some serial order. Now, they're not actually run in some serial order. They're performed in parallel, especially if there's no conflicts between the transactions. And what I mean by conflicts, transactions conflict if they're actually touching overlapping keys. If there's no overlapping keys and all the transactions can be run in parallel, great. Isolation is golden. If there is conflicts, well, then CockroachDB internally takes care to make sure that they're run as if in some serial order. Now, this is part of we had this mantra in early days of Cockroach Labs that we wanted to make data easy. And our opinion is some of the weaker isolation levels, they actually place too great a burden on application developers. And we actually, part of what our mission is to make building systems on top of databases easier. This means making application development easier. Take the burden away from application developers, put it on the shoulders of the database developers, such as us here at Cockroach Labs. Other important parts to know about transactions inside CockroachDB, that transactions can span arbitrary ranges. A transaction isn't limited to a single range or a handful of ranges. It can span hundreds of ranges. And this is often the case, especially if you have a table that has secondary indexes. All the secondary indexes, they're stored on separate ranges than the primary table data. So this ability to span arbitrary ranges is extremely important foundational part of the transactional protocol. And then lastly, the transactions inside CockroachDB are conversational. And what I mean by the term conversational is that you can start the transaction, the application can perform a set of operations, get the results, apply some business logic, perform another set of operations, get the results, apply business logic, all within a single transaction. There's an alternative to the conversational transactions, which you have to specify the full set of operations up front or somehow ship the application logic to the database. And these are interesting design points to do, and yet they're at odds with the way most applications are written today. Most applications, they're using databases, traditional SQL databases. They're programmed with this conversational model in mind, and we wanted to fit seamlessly in with that conversational model. So I want to give you a kind of a high level, but somewhat incorrect view of how the distributed transaction protocol works. And I'm going to, later on in the talk near the end, I'm going to actually clarify that what I'm describing here isn't precisely what takes place. But the thing that I want you to take away from this example I'm going to walk through is how we're going to bootstrap the atomicity and durability of transactions on top of the Raft primitive of atomic rights. So here I'm showing on the screen a 4-node cluster, and we have 3 ranges in this cluster. The ranges that have the black border around it, those are the Raft leaders. And now I'm going to perform this transaction. I'm going to insert 2 new keys, 2 new rows into this dogs table. When the transaction starts, it's actually decomposed. We begin the transaction, and the first step of beginning the transaction is we create a transaction record on one of the nodes. Here we're creating it on this this range, the pine. Let's call it the pine top range. That transaction record itself is replicated as well. The transaction record, each range actually has an internal key space where we can store metadata that's useful for implementing SQL. And one of those bits of metadata is transaction records. So there's this kind of essentially this transaction record space that sits within each range, and it's replicated just like all the other data. The transaction record is created when one of the 2 followers has responded. And by one of the 2 followers responded, we now know that that transaction record is present on 2 out of the 3 replicas in the range. So one responds, and then we can move on to the next step. And the next step is we write the sunny row. The sunny row goes over to the pine top range, and it's replicated and to the followers. Now, I'm highlighting sunny in yellow here for a reason. This write is still provisional. If other transactions come in and try to see what's going on here, they'll see the old version of sunny, not the new version of sunny. And this is part of how transaction isolation works. Again, I have to wait for a single act, and then I move on to the next operation, which is to write the Aussie record. And here, in order to write the Aussie record, I have to go to this other range, the lady range. We go to the leader, it replicates to its followers, and one of the followers acts, and we're act back into the gateway node. And the final step is that we then mark the transaction as committed. And this marking of the transaction committed is a single operation on a single range. It's on the range containing the transaction record. We're essentially flipping a bit. Transaction was pending, now it's committed. And this is like that part of Raft atomicity that allows us to bootstrap transaction atomicity. Right now, the transaction is committed. Another transaction comes in, try to read Aussie, it would see the new version of Aussie at this point. In order to do this, what actually happens underneath the hood is the Aussie record we wrote actually points to this transaction record. And another reader would have to come in and see like, oh, actually Aussie's committed. That's a little bit inefficient. So in the background, after the transaction is committed, we clean up all this, all the pending markers that are associated with the rows in the system. Then we respond, and the transaction is fully committed, and we're done. All right, how are we doing on time? Looks pretty good, actually. So I'm going to talk a little bit about distributed SQL execution, and we talked a lot about the KB layer. The KB layer, just to kind of refresh really quick, it allows data to be read from anywhere. It's kind of like agnostic to the location of the data. Any node in the system can read data from anywhere. But we actually want to expose where the data is because we can't abstract away from network latencies. The speed of light is real. We can't violate the speed of light. And so what we actually want to do is we actually want to push execution to near the data. And we push the execution to near the data because oftentimes the execution is actually doing something like reducing the data into smaller parts. So we decompose the SQL query into parts along the data boundaries, and then we execute those decomposed query parts close to where the data resides. sometimes in order to do this, we have to introduce additional operators into the query execution plan in order to construct the final output. So that was like the high level of how distributed SQL execution works. First, I want to give a brief refresher on SQL execution itself. Now, SQL is composed of essentially a couple of, dozen or so relational operators. The primary ones I list here. We have projection. What projection means is you have a set of columns in a table, and I want to reduce that to a smaller set of columns or a derived set of columns. We have selection, which is filtering. This is the where clause. You have aggregation, where you aggregate the contents of many rows into a smaller subset of rows. This is group by. You have join, where you take two tables and you join them together in some fashion. And there's variance, there's union, there's intersect. And then you have just scanning from a table, reading rows from a base table. And lastly, there's actually a non-relational operator in here. Sort is non-relational, but it's also an operator. These operators are all connected in a pipeline, essentially a tree, and the results flow from one to the other. I'm going to further kind of expand on this with a simple example. So we have a very simple query here, which is reading the name column from the inventory table. And you can just consider this as being that inventory table that I showed earlier in the talk. Now, there's always a naive execution plan that can be applied to SQL. And usually the naive execution plan is pretty easy to understand. You always start from the table. So here, I'm reading from the inventory table. I can scan the entire inventory table. This might be 1 million records. I scan them all. Those results then can get placed into a filter operation. And this filter operation only passes through the rows that match the filter. Lastly, I send them into a project operation. And that projects out and only sends through the name column. And then we send on the results. Now there's some interesting bits here, which is, I could reorder 2 of these steps. I could have done in this case, the projection before the filter, and that might have been desirable. Another interesting thing is, well, we could have actually, if there's an index on this table, like that name index that I showed earlier in the inventory table, we can actually do something better, which is to push that filter into the scan. If I use the name index, well, I don't even have to scan the entire table. I can scan a fraction of the table, the fraction that contains inventory items with names that start with B, and then, names that start with B. So in this case, we could push the filter into the scan, and then we project, and then we get the results. And this is going to be much more efficient. Now, SQL execution is all concerned. It's given essentially this query plan. Oh, I'm going to scan the inventory table, then I'm going to project. So SQL execution is only concerned with this. It doesn't actually build the query plan. That's about SQL optimization, which I'm going to talk about next. But you can see from this, there's kind of like, even in this simple case, there's 2 possible query plans. In complex cases, there could be thousands of possible query plans. There's also, I've shown you these operators, the scan operator and project and filter, then there's join, but there's also tons of variants of these. There's lookup joins, there's merge joins, there's group by, but there's also streaming group by. We have to spill to disk. SQL execution is actually a very, very complex topic, and this is happening on every query, so we want this to run, blindingly fast. Now, what about distributed SQL execution? We're a distributed SQL database. How does SQL execution change when we get into geo-distribution? And really the most important thing to understand is those network latencies. We have to be mindful of the network latencies. Like conceptually, you could imagine SQL execution within a distributed database is just run the SQL execution on a single node, it pulls all the data it needs to that node. And yet that is prohibitively expensive. So what we want to do is push the execution as close to the data as possible. Let's run through an example of what that looks like. In this case, I'm using a group by operation, a streaming group by operation. So here, just imagine there's a customers table, and I want to count the number of customers by country. So I'm going to group by country, I'm going to read from the customers table, group by country, and count. Now, if we actually had the data for these customers geo-distributed, by these locations, what we'd actually do is decompose the query so that we're actually doing 3 independent table scans, 1 in each region where data is located. Within each of those regions where the data is located, we then schedule a group by operation. And this is only grouping by that data that's local to the scan. So we did the scan, and then usually on the same node that was performing the scan, we do the group by. That, in this case, likely reduced the amount of data really significantly. It could be an order of magnitude smaller amount of data. And then we send that data, that intermediate group by data, back to the gateway node that was performing that query. And that gateway node takes that input data and does another group by operation on it to get the final result that's sent to the user. And I hope this gives like some sense of like, in this case, we're taking much more advantage of the aggregate CPU within a cluster, which is beneficial. And then we're also dramatically reducing the amount of data that's sent over wide area network links. That's just going to reduce the network bandwidth. In other cases, it can reduce the latency as well. We have actually much more significant optimizations that take place for distributed SQL execution nowadays. There's systems like locality optimized search, which I'm not going to have a chance to get into. We have 2 academic papers that are written about CockroachDB. And if you're interested in some of this stuff, the most recent one that's written about some of our new multi-region primitives gets into some of these more advanced optimizations of what we do for optimizing distributed SQL execution inside a geo-replicated database. All right, so that was execution. Let's talk a little bit about optimization. Now, execution and optimization are kind of a matched couple inside any SQL database. You need to execute SQL queries. SQL queries is all about taking the query plan, as I described earlier, and running it to completion. Optimization is about taking SQL. SQL is, textual language, transforming that SQL into a query plan. It's doing semantic analysis to make sure that the SQL is valid. It's looking up metadata, making sure that tables exist, the columns exist, that you're doing operations that semantically make sense, that the types are all sensible. And then it's also doing various lookups for stats and other metadata that are going to be useful for planning. There's a series inside a query optimizer. What it's actually doing is it's taking essentially what the naive query plan that we produce and then applying a series of transformations. And there's now hundreds of transformations inside CockroachDB that it performs. The transformations, we describe them as being either cost independent or cost dependent transformations. CockroachDB is a cost-based SQL optimizer. And I'm going to run through an example of why cost is important. We have some transformations, though, that are cost independent. This is actually the vast majority of transformations. The vast majority of transformations, it doesn't matter, what the data looks like in the system. You want to perform it regardless. I'll give an example of that is constant folding. Another example of that is filter pushdown. It doesn't matter, what the cost of doing these things are. You pretty much always want to do them. Some of the cost dependent transformations, index selection, join ordering, there's a number of them. I think there's only a dozen, maybe 2 dozen of these cost-dependent transformations, but it's extremely important to do this because there can be a vast difference in the eventual runtime of a query based on the data that's contained in the tables that you're querying. So kind of like the canonical example of cost-based transformation is picking an index. And just to give you a little sense, a little taste of why this cost actually matters. There's actually multiple factors that go into index selection. What filters and join conditions are present in the query? If the query has a required ordering, such as an order by clause, if a query has an implicit ordering that could be taken advantage of by a specialized operator, this is true for group by, whether the query is accessing an index that's covering. By covering means all the columns in the query are actually contained within the index versus a non-covering index where I'm actually going to have to go and look up the primary table data. And also the locality. The locality of where the data is affects the selected query plan. So I just want to run through an example, and this should give you some understanding of how cost comes into the query plan selection. So here we have a query. It's reading from a table A, it has a filter, filtering out the rows where X is greater than 10, and then I'm sorting on the column Y. So the naive query plan for this query would be to scan the primary index, then I filter the rows I want, then I sort the rows. Now, the thing to understand here and why cost is important is this sort operation, it could be very fast. This might be a good query plan. If there are a few rows, the sorting is just going to be essentially free. You have 10 rows to sort, it's like no problem to sort the 10 rows. If you have 1 million rows to sort, wow, okay, let's maybe figure out a way to reduce the number of rows to sort. So here's another query plan. Let's say I have an index on X. Then I can push that filter right down into the scan operation. And then I can scan, then sort. Well, there's actually another possibility here. Perhaps I have an index on Y. The index on Y will allow me to scan Y and get them in sorted order, and then I can filter. Which one of these do I want to do? Well, it kind of still depends on the data. Now, that second query plan, the one I'm scanning from X, let's say I do that scan and the filter is really selective and only 10 rows come out of that scan. Then I'm only sorting 10 rows. That's most likely the lowest cost operation. I mean, in this example I'm showing right now with the table sizes, I'm saying there's 100,000 rows in the table. If I scan X, I get down to 10 and then I can sort them. Or if I scan in Y, I'd still have 100,000 rows that I'd scan from at Y index, and then I'd have to filter them. Okay, so the scan then sort is the quickest. But the table data might be something different. It might be the case that I do that scan on X and there's 50,000 rows, and then I have to sort 50,000 rows. And sorting's an n log n operation. The higher n is, the slower it's going to go. And in this case, it's very likely that, because the filter isn't very selective, it'd be better to scan and not have to do the sorting at all, and then scan then filter. So I hope, the takeaway from this is just that even for something as simple query as this, that actually incorporating cost and statistics about actual data distribution inside your tables into the query optimizer can make a significant difference. And then for more complex queries involving joins and group bys, this even becomes more and more important. All right, moving on. Last section, we're going to talk about distributed performance optimizations. And primarily going to be talking about how the transaction protocol I described earlier, it was inaccurate. I mentioned it was inaccurate, and now I'm going to describe how that isn't actually what we do. We have 3 additional optimizations on top of that kind of base protocol. 2 of them are described here. One of them is lazy transaction records. And the idea behind lazy transaction records is that we can actually avoid writing that transaction record. I described it's the first step. The first thing we do is we go and write the transaction record. We can actually avoid creating that transaction record and deferring it until sometime after the transaction starts. And just the existence of pending write operations proves the existence of the transaction record. In very common cases, majority of common cases, if a transaction is short-lived, we end up never writing the transaction record, which is a benefit. The second optimization is write pipelining. And the idea behind write pipelining is when I talked earlier in that base protocol, I would write a row and then I'd wait for its acknowledgement. I'd write another row, I'd wait for its acknowledgement. Well, if you're writing a whole bunch of rows, that's a lot of round trips. And it's much better if we just allow all those row writes to go out and then wait for the in-flight writes before commit. And this occurs not just on single statements, it occurs across multiple statements within the same transaction. And there's a complexity here that transactions want to be able to read the data they've written. So if you actually end up reading the data previously wrote, there's something that's akin to a CPU pipeline stall in order to wait for the data to be written. I'm just going to walk through that same transactional operation we had before. We start a transaction, we write 2 rows. Serial model, we write the transaction record, wait for it to acknowledgement, write the Carl record, wait for its acknowledgement, write the Nigel record, wait for its acknowledgement, and then finally we mark the transaction as committed. Important thing to understand here that's going to become useful to understand in subsequent slides is that transaction record we write, it actually knows what rows, what keys we were touching. But as you can see here, we did 4 network round trips. Now with the lazy and pipelined optimizations, this gets dramatically reduced. We write the Carl record, because we never had to write the transaction record at the start. Then we wrote the Nigel record. Then finally, we actually write, we wait for those to finish, and then we write the transaction record in committed state, and we wait for that. Now we've only done 2 network round trips. And that delta is significant latency savings. In fact, this is the common case when we introduce this, that you get down, you see just 2 the latency for transactions was 2 network round trips. And it was pretty marvelous. You add more distribution, more statements, and it still stayed at 2. But we can do better. And that better was our big final optimization to our transaction protocol, which is this idea of parallel commits. Now, the parallel commit stuff, this is also talked about in one of our papers, academic papers. It's a little bit of a mind bender, but the kind of mental model I have for it is previously what we had is a single kind of transaction commit bit. Every transaction has a single bit, and in order for a transaction to commit, we flip that bit from on to off. But we can actually have essentially what is a distributed indication of whether a transaction is committed. And that distributed indication is whether all the operations have finished within the transaction and the transaction record has been performed. And by doing this optimization, we reduce the latency to 1 round trip in the common case. I'll just kind of give you a quick visualization of the way this works. So you see the serial operations on the left here, and here's on the right, the lazy pipelined and parallel version of it. We write the Carl record, we write the Nigel record, we write the transaction record, and the transaction record refers to the keys that were previously written. And then we do a single wait step that waits for all of them to complete. And this essentially, we see in our graphs that, this has reduced the network round trip time to essentially 1 network round trip. After this is done, we then go and do some asynchronous cleanup in the background. We actually took the effort to go and prove that this was correct with a theorem prover, TLA plus. And this gave us a lot of confidence that what we did was viable before implementation. All right, moving to the final stages now. So I was kind of describing the base architecture of CockroachDB, but there's a whole lot more that goes into building a production database. CockroachDB is Postgres wire compatible. We're actually very compliant with PostgreSQL. We have systems like change data capture because CockroachDB doesn't sit in isolation. In modern application architectures, you need to be, sending the data inside your, system of record to analytic systems. You need to sometimes be sending them to other databases. We have a whole bunch of management facilities. There's a web console. We perform rolling upgrades. There's backup and restore, of course. We integrate with Prometheus. We talked about the optimizer, but we also have query inspection facilities, online schema changes. And there's a whole bunch of stuff around security, which is just, table stakes nowadays. And then, these things seem a little bit mundane, but like table stakes is really the way you should view them. You need these things to operate in enterprise environments and production environments. I also want to highlight some stuff that's outside the product, but also extremely important. We have world-class documentation I'm extremely proud of. We hired our first doc writer really early in our lifetime, and it's been one of the best decisions we made. And we've since expanded that documentation effort to include free online training via Cockroach University. And then the final piece to call out is that we have a world-class services and customer support department, which I'm extremely proud of. We frequently get called out for how awesome our customer support and our services department are, and that's because we invest in them heavily. All right, well, we're at the end.
Peter, you made it. That's a lot of architecture. Just one point, everybody. On the last slide, we talked about you mentioned backup and restore, CDC, change data capture, these sort of things. I think in Cockroach, those things too have to be distributed, right? You aren't going to emit a change feed from one place. You're going to emit it from every single node. So even those concepts, even around security, everything had to kind of be.
Yes.
Rethought, right?
You do distributed. Distributed isn't one isolated thing. It's something that pervades the system. Distributed backup, distributed restore, distributed import. Distributed is like, it's like this prefix on every system that we have.
Yeah, and I think it's just one of these things. And there was a lot of questions here, and I'm gonna lob a couple of them into Peter. I paraphrased a couple of them down and into a couple of different categories here.
Yep.
I think when you do start thinking about distributed systems, there is just a lot to be learned here. I think there's a lot here to glean from this presentation to apply your own. There was just there's a question. I'll try to paraphrase it. The concept of time in a distributed system is actually pretty important. And we talked a little bit about serializable isolation, and what that means is basically things are going to happen in order, right, Peter?
Yep.
How do we deal with time? In a distributed system, each piece of hardware, the clock on your laptop right there, I'm sure is off by a couple milliseconds than what's here, right? So how do you deal with that in CockroachDB?
Yeah. Unfortunately, this is a complex topic. I'll just give a kind of a brief summary of it. For those who are interested in hearing more about this in depth, one of, I think, the most viewed blog post.
Absolutely.
Is this blog post written by the man you see on the screen right now, our CEO, Spencer Kimball. He's actually quite technical. But he wrote a blog post called Living Without Atomic Clocks, and describes some of how time works within CockroachDB. And also, I would again point you to our academic papers. I believe the first one actually talks more about this in depth. Essentially, we rely on some form of clock synchronization taking place between computers. But it's important to understand that clock synchronization isn't perfect. There's always going to be some amount of delta between the clocks on different machines. And what the clock synchronization protocols are doing, like NTP, they're trying to maintain that within some certain bounds. If you have kind of more advanced systems, and famously Google has this with Spanner, you can actually get the clock synchronization down to millisecond level. That's what Spanner publicized in their paper. I believe, I've heard rumors that it's actually lower than that. And then there's other companies that are reducing it even further. There's a company, Clockwork, I believe, that now has it down to, microsecond levels. There's an effort coming out of Meta to actually have, better synchronization hardware. But synchronization is one aspect. And then there's the aspect of how do we actually use time throughout the system. And what takes place here is this thing that I didn't talk about, which is our multi-version concurrency control. With MVCC, every record that we write to the system has a timestamp. And we're actually looking at that timestamp to decide what was written before and what was written after. One of the big complexities, though, is because we don't have perfect synchronization of clocks, we have to worry about what happens if two timestamps are within that delta of uncertainty. And there's some complexities. And this is where I would point you to, for more information, go read Spencer's blog post for what we're doing there and how we're reacting. And we actually take a somewhat different model than Spanner. In Spanner, they actually, they see the uncertainty window and they wait during writes. We do something different because our uncertainty window is higher. We actually wait during reads. So the writes go forward fast and the reads get paused. Generally, this is a good trade-off for us. There are some advantages to having a tighter clock synchronization. This is an area of active improvement that we're working on in the system.
Yeah, and so you answered the other question, was like, how do we deal with conflicts and whatnot? And I think understanding, MVCC is a great place to check that out. I always like to drive, funny enough, the Wikipedia article about MVCC is like super solid. I really kind of, I would go there and start there. There's been other presentations we've done on this, but I think it's a great concept to understand.
I agree. The Wikipedia article on some of these things are great. They have a good one on Raft as well.
They do.
So something else to point out, MVCC is one aspect of how we deal with conflict. There's other aspects. We actually have pessimistic locking inside CockroachDB right now, and there's a lock manager, and there's we lock not at the range level, but there's spans of keys that we lock upon, and there's queues. If one transaction is conflicting with another, they'll actually, that second transaction will block, waiting for the first one to complete. We started out the CockroachDB, our initial implementation, had something called optimistic locking, where we just try to deal with these things at commit time. And that actually has really poor performance when there is contention. So since we improved it with this kind of pessimistic locking, this upfront locking, which actually gives you much more predictable performance when there is contention.
Yeah. There was a couple, actually, this is the first time I've ever gotten a couple questions on this topic, but people are asking about joins, how it works. How does that affect performance of the overall database in the context of other queries that are going on, let alone just the join? This is an area that I'm not too familiar with as well, Peter. I mean, what are some of the complexities that we had to actually kind of encounter in doing, joins across the distributed system?
Yeah. Well, I think there's two aspects to this. One, joins are the prototypical example of how optimizers are very complex.
Yeah.
And what happens is, if you have a multi-way join, kind of the state of possible query plans that you're looking at explodes dramatically. And it gets to the point where the optimizer is taking way too much time to optimize. We actually have a pretty sophisticated algorithm, kind of state-of-the-art algorithm we adopted from academic research for how do we actually explore that join space inside CockroachDB. After you actually get the query plan, what join order you're going to do it within, then it's how to execute it. And this is part of distributed SQL execution that I didn't get into. Well, we want to do, you want to scan the data, from the base relations, but then it's actually sent to other processors nearby. But this is fan out. The join doesn't just occur on one node. we're actually scheduling join operators for a large query on multiple nodes next to the data they're utilizing. So, there's this, the scan operations are feeding their data into join operators, and those join operators are feeding into other operators that are kind of further joining the data together. How does this, affect the overall performance? I mean, the operations that are being performed, it's all just kind of SQL. They're all like decomposed SQL operations, but joins are just like you're doing kind of more of this stuff.
Right.
I think the thing to understand though is if you're not having this done in the database, you're having to do it at the application layer. And I've seen this happen plenty of times. I've written this code myself where I'm essentially doing the join myself in the application code. And all I can say is whenever I've done this in application code, whenever I've seen it in application code, I'm doing it much less efficiently than what the database is doing. So you want the database to do it. The database is doing intelligent distribution. It's deciding between the various possibilities for how to execute the join. Am I doing a lookup join? Am I doing a merge join? Am I doing some other form of join, a hash join? And it's making that intelligent decision and then distributing the operation across the database.
Yeah, and I think it's just one of these areas, let the database do the work that you don't really need to do, right? Like, I think that's such a big deal. Related to this, there was another question kind of early on, Peter, and it's kind of related in the same sort of thing. So what about things like counts and sums and that sort of stuff, right? Like, I just want to say, I'll give a good example. I want to sum how many widgets I sold in a day or whatever that is. Mm-hmm. Are you doing full range scans of the whole table? Are you doing push down? How are we dealing with that in Cockroach as well? Because I think that's from a distributed point of view, it gets pretty complex, right?
Yeah, it does get complex. And this is like, the magic of SQL optimizers.
Right.
So let's say, you want to do that example. You want to count the number of widgets you sold on a particular day. Right. If it's a particular day, well, you have constrained it so you don't have to scan your entire table. That's great. Let's say it's not on a particular day. When you want to sort it on the past 3 months, well, maybe that is a small fraction of your table still. If you have a year's worth of data in your table, it's only 3 months, you still constrained it. But even if you have to scan the entire table, well, you're getting the entire aggregate resources of the cluster to do that scan. You're probably pushing down some kind of projection and filtering. You're filtering that out. You're doing this aggregation. I mean, you're essentially taking this entire cluster of machines and putting it to work on this stuff. And yes, actually, this is going to be expensive, but I mean, it's going to be expensive on any database. We're just allowing you to scale out horizontally. Something that we've introduced in the most recent release, in the 22.1 release that came out in the spring, is that we have this emission control facility, and we actually put quality of service controls that are tied into that. So you can actually mark these expensive operations as background operations so that they have less of an impact on foreground operations in your application. Yeah. And that's highly desirable to do. If you're going to do some big analytics operation like this, well, you're probably less concerned about it happening as quickly as possible and more concerned about it not impacting foreground operations.
I love it. You're picking off questions that actually had come up along the way.
I can read.
I know. Yeah. You are not reading.
I know.
All
my
this.
eyesight's not that good online.
The quality of service stuff gets through. But this is kind of one of those things. It's like, you can build this really cool database with all these cool things, but without like the necessary kind of enterprise-y type features that are really important, it's just a different game, right? And I think those are some of the, and they all get complicated when they're distributed. One more question. We're 10 minutes past. I don't want to hold people up too long. We talked about CBO. Are there things like plan hints and this sort of stuff in the cost-based optimizer for Cockroach as well?
Yep. No, we have plan hints. We have operator hints like join. If you want to say, I want to look up join, I want to merge join, you can put those kind of hints in there as well. We also have some other cool facilities in there that, they're in their early days, but they're already extremely useful. We have facilities that it will actually recommend indexes. If you can do an explain on a query, and the explain will tell you what the query plan is. Yeah. And then it'll also say, hey, actually, if you added this index, we can make it more efficient. And then we have the converse of that as well, which is we will tell you about indexes that are unused. Right. I mean, both of those are extremely important performance optimizations. You're missing an index, well, crap, you might be doing a full table scanning because you're missing an index, or you have an unused index that's purely just hurting your write performance and showing no benefit. Well, Cockroach will tell you about both of those.
And again, I think one of these kind of areas of maturity where we're learning as well, I think the cost-based optimizer first came out a year and a half ago.
It's more than that. I think
it's more, yeah.
I think it's more like 3 years now. Oof, yeah.
And we've learned a lot, and I think we're now picking things out and making it valuable across the entire database. So, so Peter, thank you for doing this. It's funny, I'm looking at you on on the screen, I'm looking away from you, but I'm actually sitting right next to Peter. I'm happy to do things live again. So
Yeah.
thank you so much, Peter. Really, really appreciate it.
Yeah, pleasure to be here.
If there's any